Hi there, I'm David Dye and I'm going to introduce you to this course on linear algebra. Later in the course, Dr. Sam Cooper will take you through the last module, and in his course on multivariate calculus I'll do a bit in return. But in this video I just want to take a moment to introduce the course and what we're trying to do here and to set the scene. The world is awash with huge amounts of data. Most of us living in cities generate huge amounts of data as we go about our lives, moving around, browsing our mobile phones, using transit networks and consuming energy. If we just think about energy alone for a moment, our society literally lights up our planet from space. We can see where the people and economic activity are from the light. Zooming into Europe and London here, you can see how some of the world's great cities network together. This takes a huge amount of energy. And if we're going to figure out how we're going to generate and use energy more sensibly in the future, we're going to have to understand the data we have about energy much better. If we don't want to damage our health with NOx and particulates, and if we want to combat global warming, we're probably going to have to strongly cut back or even eliminate burning hydrocarbons as the leading approach to powering our society. And we can. With wind, with nuclear, with solar, we can probably make huge strides towards reducing our need for fossil fuels. But we're going to need storage and batteries in order to have hybrid and battery electric vehicles. We're going to need to insulate our buildings much better and heat them much more efficiently. But where should we start? Where are the opportunities to have the biggest impact soonest? If we install this energy saving measure, how much will it cost and how much will it help? Should we recommend that everyone buy heat pumps, or should people first insulate their homes better? How much range do electric vehicles really need? How big should their batteries be? In improving the London Underground so that more people use it and less people drive, are there stations that are so close together there's no need to stop at them most of the time? All of these questions we could answer better if we could analyse the energy and usage data we had better. If we had good models of data, then we could also make predictions. Practically speaking, we could build software that tells you how to take the fastest journey across your city and put it in an app, or which web pages you might want to see in response to a search query. And we don't necessarily need a physical model in order to make such predictions. Neural networks are very accurate in many applications at modelling data and making predictions. And the process by which we optimise those networks is called machine learning. Now it turns out that linear algebra, how to solve systems of equations like this, where the variables obey the rules of vectors like these, and then taking those forward and recasting them as matrices like these objects here, this is very important in machine learning and data science. And also, being able to do optimizations in machine learning and data science in turn depends on understanding how a thing we're trying to optimize changes in response to changes in the parameters that describe it, which is multivariable calculus. These sorts of symbols here. The problem is that machine learning and data science have their origins in computer science and mathematics. But more and more, we're wanting to use that maths by engineers and physical scientists and biologists and people working in medicine and social scientists and so on. But one of the problems is that most courses on data science and machine learning presuppose a level of familiarity with linear algebra and calculus that not everybody has. So our aim in this course and in this specialisation is to revisit the underpinnings in vectors and matrices and calculus that you may have touched on in school but which you might never have applied. Depending on how it was taught, it may not be at all obvious to you why that maths would even apply to the world of data. Usually high school maths is motivated, if it is at all, through physics, after all. So this might not be that obvious. To be clear, we're not really aiming to do a fundamentals course where we do everything very rigorously, as we would if we were trying to set up for a graduate school class in applied mathematics later. Nor are we aiming for the breadth of a linear algebra or a calculus course that would apply everywhere across science and engineering. We're just aiming to, very quickly and in a way strongly motivated by machine learning problems, give you enough underpinnings to get you going. And more than anything else, we want to develop your mathematical intuition. That is, we have computers to do all the mathematical operations for us now, in Python or MATLAB or R. And some of the most complex exercises at the end of these courses will ask you to write some very short little mini blocks of code in Python to develop and demonstrate and use the mathematical insight you've developed. But doing the operations and crunching through them with pen and paper, plugging the numbers and chugging your way to the answer, it's just not a very useful skill in the world anymore. So our focus is on the ideas, not on your endurance. So linear algebra is defined to be the study of vectors, vector spaces, and mapping between vector spaces. It emerged from the study of systems of linear equations and the realization that these could be solved using matrices and vectors. So the first thing we'll do is look at vectors and the operations we can do with vectors. And then we'll move on to look at matrices, and then in the final module we'll put it all together with an application to Google's famous PageRank algorithm for ranking web pages. So that's what this course, Linear Algebra, is all about, and how it relates to the other courses in this specialisation on multivariate calculus and machine learning. So welcome.